Okay, I'm going to try to give you a quick crash course on absolute extrema, Rolle's theorem, and mean value theorem, so that tomorrow during class we can just practice. So real quickly, if you know it, skip over it. Absolute extrema I touched on quickly in class today. And the idea with absolute extrema is the problem is going to ask you for the absolute min or the absolute max. Or they might ask for a max or a min on a closed interval. Once you see that closed interval, that is your clue that, oh, they don't really want me to find the critical values, make a number line and test. That finds relative maxes and mins. Now they want me to do that, find critical values, but they want me to include endpoints because it's possible that one of those endpoints might be our biggest or our smallest value, our absolute extrema. So I gave the really simple explanation today of a parabola, but I can still use that. If I have a parabola like this, and I'm given endpoints here and here, well then I understand that I have a relative min here. And if I didn't have endpoints, this went on forever, I would not have a relative max. But once they put endpoints on, I now have an absolute min and I have an absolute max. And the way I find out where they are is I take the derivative of my function, whatever that equals, I set that equal to 0, and I find out where that derivative is undefined, because maybe I have a graph that looks like this. I figure out where the derivative is 0, where it's undefined. I don't make a number line now. What I do instead is I make basically a t-chart. I do it on its side. I don't know, it's just a habit I've gotten into. I take all of those critical values and the endpoints. So I take the critical value of, let's say over here 1, and then I take the endpoints of, let's say this was -2 and 3. I take those critical values and I plug them into the original function, and I find out the y values that go with them. So let's say this critical value had a y value of -2. Let's say this critical value has a y value of 3, and this critical value has a y value of 6. If they wanted to know where is your absolute min, I would say in this case my absolute min is at this x value. So the absolute min is actually referring to how low does it go? Sorry, that's annoying. How low does my graph go? What's the smallest y? So since my absolute min is happening here at 1, my smallest y is -2, so my absolute min is -2. And my absolute max is what's the biggest y? And that was happening over here at 6. So my absolute min is -2. It happens at the point 1, -2. Absolute max is 6, and that happens at the point 3, 6. Okay, so you can go through the math, and we'll do one as we do practice, but that's your quick course on absolute extrema. And now let's go into Rolle's theorem and mean value theorem. So they're basically the same thing. Rolle's is actually a more specific example of mean value theorem, but we usually start with it because it's pretty easy to understand. Rolle's theorem says, if I have a function and that function f is both continuous and differentiable. Okay, so that is key. Whenever I use Rolle's theorem or mean value theorem, I need to state that the function I'm looking at is continuous and differentiable on the interval that I'm given. So if f is continuous and differentiable on some interval, let's say a to b. So let's put a over here, let's put b over here. Rolle's theorem says if the y value at the one endpoint is the same as the y value at the other endpoint, then somewhere in between a and b, the derivative of the function must be 0. So maybe the function goes up and comes back down, and my derivative is 0 here. Maybe my function goes down, up, and down, and up. Well, then I have a derivative of 0 here, here, and here. Maybe my function just goes straight across. Well, then the derivative of the function is 0 everywhere. But Rolle's theorem says if my y value at the one endpoint is the same as the y value at the other, then somewhere in between there has to exist at least one value for x such that the derivative is 0. The way that's written fancy is if f is continuous and differentiable on this interval, then there exists a value c on AB such that the derivative, oh, whoops, I forgot one little thing, hold on. Such that the derivative of f at c equals 0. So sorry, if f is continuous and differentiable on AB and f of a equals f of b. So my two endpoints have to have the same y value. Then there exists a value c on this interval AB, so in between a and b, such that the derivative of f equals, or at c equals 0. This is the fancy calculus way to write it up. If you were looking in a book, that's how it would be written. So if I'm doing, if they ask me about a problem with Rolle's theorem, and I have some value for f of x, I have some function, let's see, I think I have one here, x squared plus 3x plus 2, if that's my function, and they give me an interval of 1 to 2, I want to first decide, is this continuous and differentiable? Yes, it's a parabola. I want to find f of 1, and I want to find f of 2. I'll do the math for you. In this case, turns out they're both 0. So since f of 1 equals f of 2, Rolle's theorem applies. It means there must exist some value between 1 and 2 such that the derivative of this function equals 0, or such that this function will have a horizontal tangent line. So I don't need to go further unless they ask me to find that value of c. If they do, well then I take the derivative of f, I set that derivative equal to 0, I get negative 3/2, and that is the x value. And look, oh wait, whoa, poop. Ah, crap, sorry. I was like, uh-oh, this is supposed to be minus. Minus, so then this is positive. Okay, so there's my x value, it's 1.5. Yep, it exists. There's my value between 1 and 2 such that the derivative is 0. Beautiful. So I didn't check my math, but if you were checking me, you would have been like, wait, no, the y values aren't the same. Yep, they are. I just didn't have that as a minus. Okay, so crash course number 3 is mean value theorem. So mean value theorem is really similar to Rolle's. Mean value theorem, though, doesn't require equal y values at the endpoints. So I have a function from a to b, but now instead, let's say a is here and b's up here. Well, the mean value theorem says if I find the slope between a and b, whatever that slope is, the derivative of the function must have that same value somewhere between a and b. So that means if my function goes like this, the slope between a and b is modeled by this line. Well, the derivative of the function has to have that same slope, or the tangent line of the function has to have that same slope somewhere between a and b. It looks like if I think about a tangent line, I wish I had I have a ruler. Here's a ruler. If I think about moving this ruler along the curve, maybe right there, maybe right here, my tangent line has the same slope as this line. Therefore, the derivative of this curve has the same value as the slope of this curve. And it probably happens again. Let me continue along the curve. My curve changes. Now I have a negative slope. As I continue along the x-axis, now I have a 0 slope. And now my slope is back to positive, and maybe around here, around here, I have another tangent line with the same slope as that line that connects A and B. The line that connects A and B is called a secant line. If you remember from geometry when you did circles, that was a secant line, that was a tangent line. Okay, so this line that connects A and B is called a secant line, and the mean value theorem says that the slope of this secant line that connects the two endpoints has to be the same as the slope of the curve, of the tangent line to the curve, somewhere between these 2 points. It really is the same thing as Rolle's. It's just that for Rolle's theorem, that secant line was horizontal. The line between A and B was horizontal, so the slope of that line was 0. here, the slope of this line will be something you have to calculate. So you're going to have to calculate the slope between the endpoints. And mean value theorem is going to say that this equals the slope of the tangent line somewhere on the interval. So how do we find the slope between two endpoints? Well, we do the y minus the y over the x minus the x. So the slope between the two endpoints will be f of b minus f of a. That's how we label y's. And b minus a, x minus x. This has to equal the slope of the tangent line, or the derivative, at some value. Again, we're going to use the letter c. So mean value theorem says if f is continuous and differentiable, okay, it has to be continuous. I can't have any spaces, and has to be differentiable. I can't have any corners or cusps or funky stuff going on. Otherwise, things get messed up. Like if I have a function like this, can we still see that? And let's say I go this point and this point. Well, the secant line is going to have a slope of 0, but I never have a slope of 0. Here at this cusp, the derivative is undefined. The slope would be undefined. I'd have a vertical line at the tangent line to this cusp, so that it wouldn't work out. So I need the function to be continuous and differentiable. So if f is continuous and differentiable on some interval a to b, then there exists some c on AB such that the slope between the endpoints equals the derivative of the function somewhere. So in this case, we're going to have a little bit of computation to do. Let's say you had the same function as up here, but now we had different endpoints that gave us different y values. So now let's say the endpoints were 1 and 4. Oops. Now I'd have to find the slope between them. I'd have to say f of 4 minus f of 1 over 4 minus 1 and see what that gets me. It'll get me a number. So f of 4, I don't really feel like doing this. F of 4 is going to give me a number, 16 minus 12 plus 2. F of 1 is going to give me a number, 1 minus 3 plus 2. Or 4 minus 1 is going to give me 6/3 or 2. This is the slope of the line between the two endpoints. And then I'm going to take the derivative, 2x minus 3. And instead of setting the derivative equal to 0 like I did in Rolle's theorem, I set that derivative equal to the slope between the two endpoints. And in this case, I'm going to get 5 over 2, or 2.5, which, yes, is within that interval. Okay, hopefully that all makes sense. In class, we're going to do some work.